All right, let's get started. Good morning, everybody. Time for another exciting morning of chemistry with me, your host, Dr. White. All right, today we'll be doing the lab. It's on Zoom, on Labster, and just go on there, work through it, try and do at least one problem, answering it, and you'll get your 11 points. All right, but I should teach you what's going to be on that lab. So let's get started. All right, today's lab deals with ionic and covalent compounds. Now, ionic compounds, when you put it in, first of all, they're ionic because they form ions. And because of that, they conduct heat and they also conduct electricity. And in today's lab, you'll measure conductivity. Now, the other thing ionic compounds have are high melting points, extremely high melting points. In the order of greater than, I'm guessing now, 500 degrees C, which is close to over 1,000 degrees Fahrenheit. Now, covalent compounds do not form ions. They're from covalent bonds, which you learned about from your friendly neighborhood chemist, me. I should have put up here. Which I did. Now, when you put a covalent molecule into water or just test it alone, it's not conductive. Or it doesn't, you can't measure under any conductivity. And unlike ionic compounds, which have a high melting point, covalent compounds have a low melting point. I'm guessing now, but from my experience, most of them are the melting points are less than 300 degrees C, usually about 200, 100, even lower. And today's lab, what you'll be doing is on Labster, you have two unknowns, and you'll be testing for conductivity. And if it's has conductivity, conducts electricity, it's ionic. If it does not conduct, it's covalent. You'll also do a melting point. The melting point is high, it's ionic. If it's low, it's covalent. Now, what's the melting point? That's the temperature at which a compound, a molecule, when it's in a bulk form, goes from solid to liquid. Again, melting point is when it goes from a solid to liquid. Example, water, when it's frozen, we call that a solid ice, melts at 0 degrees C to make a liquid, which we call water. And why they have ice and water instead of saying it's a solid liquid, I don't know. But that's a very low melting point. Now, sodium chloride, and through the miracle of the internet, and this is Wikipedia. I don't know if I mentioned this before, but I should mention it now. Wikipedia, I don't know about other things, when it comes to chemistry, especially organic chemistry, but most chemistry things, over the years have been so heavily policed by people like me. Yes, I have the credentials, and I have made major changes in Wikipedia posts that were wrong, that for many years now, I have not seen anything really wrong in chemistry. Other stuff I can't say, but for chemistry, it's spot on. And let's go to the Wikipedia entry for sodium chloride, NaCl, which is an ionic compound. And Wikipedia has it set up that if you scroll on the right, you see certain physical properties. And if you notice melting point right here, it's, wow, 800 degrees, a little over 800 degrees Celsius, which is 1,473.3 degrees Fahrenheit. Wow, 5 significant figures. It's a pretty accurate measurement. And what that means is, I was telling you the truth. Ionic compounds have high melting points. Now, if we look at another one, let's do one. Sucrose, which you know as table sugar, is a covalent molecule. And if we look at the physical property, it decomposes at 186, it breaks down. So that means it really doesn't melt, but it still has the melting point very low. Let's try another one just that doesn't decompose. This is called benzoic acid. And benzoic acid is reacted to make a chemical that's used as an additive in your pop. By the way, I'm from the Chicagoland area, and stuff that comes in a can or bottle with bubbles in it and very sweet and non-alcoholic, we call pop, not soda. But derivative, something made from this, if you notice the melting point for benzoic acid, which is a covalent molecule, is 120 degrees C, 252 Fahrenheit, which is a heck of a lot lower than 1470 whatever Fahrenheit. So ionic compounds, high melting point, covalent molecules, low melting point. And this is what you'll be measuring. Now, one of the things you're not familiar with, and in real life, if you were at COD, we wouldn't be using, but to impress people, Labster uses one. And in research labs, I've used it. Oh, by the way, warning, it's time to find out why Dr. White never had any hopes of ever going to art school. My mother was a very good amateur artist. I have a couple of her pictures, but me, yeah. By the way, it's permitted to laugh and fall, but don't fall off your chair. Time for some artwork from Dr. White. Now, one of the things you'll be using in the Zoomster lab is called a magnetic stir. Here's a beaker. If it has a liquid in there, a magnetic stir has a base with a little knob here, and it's electrical, so you plug it in. And in here, there's a motor that has a magnet. And when you turn it on, this spins. Now you put in here another magnet, and that's looks like this when you blow it up. And there's a magnet, and here it's coated in Teflon. And when this spins, and this mixes the material in there. And they have you use it. I don't know why, but they do. And it's how you mix a solution. You got to figure out, put in the magnet, turn it on, put in your compound, put in some water, mix it, and put it back. Took me a while, about a minute or two to figure it out. But anyways, you'll also have a conductivity meter and a melting point apparatus. But the key thing is just try it out, try to do a couple questions, or at least one, you'll get your 11 points. All right, any questions on the Labster Lab? Remember, always feel free on Monday and Wednesday nights to go to my office hour at 6 p.m. Quick commercial for me, Dr. White. Don't forget, or actually it's more a public service announcement. Don't forget, I've changed the syllabus. Test number 2 is not this Thursday. It's a week from this Thursday. I'm glad I moved it, because otherwise I'd be rushing and we'd have to finish today or tomorrow, and then you'd have the test on Thursday. That's not fair to you, and that's not who I am. All right, it's time to get back to some chemistry. And we're talking about mass calculations for reactions. And when you have a reaction, a balanced chemical equation, you can use that to determine various amounts of chemicals you have to mix together to make a certain amount of a product you want. And one of the things you should remember, and let me open up something I didn't open up that I should have. All right, something you should remember. 1, mole of an element equals Avogadro's number of that element. Mole of a compound equals Avogadro's number of molecules, Avogadro's number being 6.02 times 10 to the 23rd. A mole of an element equals its atomic weight in grams. A mole of a compound. And for my class, since I worked in the real world, it turns out this is quite important, and this is quite important. You should know 1 mole of a compound equals its molecular weight in grams. And the molecular weight of a compound is the sum of all atomic weights in that compound. So let's look at a problem. Let's do this is not what I want. This is what I want. All right, let's do a new problem. And let's check 6, 6, 2, 2. We have a balanced chemical equation. And say sometime in the future on a piece of paper or on a file, because I don't hand out tests, obviously, you'll see a question, 10 points. How many grams of nitrogen, N2 is nitrogen, are needed to make 376 grams of ammonia? And you're also given a balanced chemical equation. So the first thing you should do, and I'm going to let you try this out yourself, is what are you being asked to find and what are you given? That's all I'm asking right now. All right, time's up. What are you being asked to find? Grams of nitrogen. What are you given? And the nice thing about doing this is, once I do this, I never have to look at my problem again because I have all the information I need. Now, there's no way I can go from grams of nitrogen to grams of, or from grams of ammonia to grams of nitrogen. What you need to do is use this. For mass calculations, mass means weight and weight is grams, you need to do 3 steps. Whatever you're given the mass of, A, in this case ammonia, you have to convert to moles of ammonia, A. Once you have moles of A, you convert to moles of what you're trying to get to, B. But you're being asked to find grams of B, so now you have to convert moles of B to grams or mass of B. This will be given to you. And same thing here. An important thing, like I mentioned earlier, you should remember, but I will give this to you. In the past, I used to make students memorize this. I don't anymore. And that is 1 mole of a compound equals the molecular weight of a compound in grams. 1 mole of a compound equals the molecular weight in grams, and the molecular weight of the compound is the sum of all atomic weights. So now we have to do the 3 steps. First one is whatever we're given, we have to go from grams to moles. What are we given? The grams of in this case, ammonia. So what does that mean? Well, this is the only number we have to start with. And if I could convert it in one step, what units do I want to get to? Moles, in this case, moles of ammonia. Oh, I have to do it. And it's time to use your good buddy, your good friend. I love that. Unit analysis, and really unit analysis has been my good buddy and good friend for many, 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 many years. So let's use it. How do you use unit analysis? Time for Dr. White to go Technicolor. I just did a generation gap thing on you. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. Therefore, on top, I want moles of ammonia. Underneath, I want grams of ammonia. And where do you get that relationship? One mole of a compound equals its molecular weight, MW in grams of the compound. And the molecular weight is the sum of all atomic weights. So if we look over here, you have 1 nitrogen, 3 hydrogen. Remember, on my test, use 3 significant figures for all atomic weights. You got to round it off. Nitrogen is 14.0, hydrogen 3.31 point. I got ahead of myself. Remember, when you're adding, you have the same number of significant figures past the decimal as the number with the fewest. This is 1, this is 2. Round this off to 1, keep that. That's 4 or less, I drop it. So for every 1 mole, you have 17.0 grams of ammonia. And now, before I do my math, I'll say grams of ammonia divided by grams of ammonia equals number 1, because anything divided by itself equals 1. That cancels out. I'm left with what I want. And now it's time to get to my calculator. Hang in there. I thought I had it saved somewhere. I'm formatting cells now. And now we come here and we say 376 divided by 17.0. All right, hold on. All right, hang in there. I don't know why this is not liking me today. All right, let's try something else. All right, that's weird. Usually I only have to do plus. I've somehow managed to change my spreadsheet. All right, let's do this. We get this number, three significant figures would be 22.1. Remember, I have formatted, that's why there's the extra zeros. Just ignore it for now. Remember that there's two ways of rounding off. Wait until the end or each step. I'm an each step person, but I also will calculate if you're do it at the end type person, because I'm not going to force you to do one way. So let's go back to our problem. So we know how many moles we have. And now it's time for step number 2. That's moles of A to moles of B, where A is what you just figured, 22.1 moles of ammonia. What are we trying to get to? Grams of nitrogen, but at this point, we'll use moles. And since I already did it once today, I don't want to burn you out. It's time to use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. And in this case, on top would be now I have bad hair days. I'm having a bad writing tablet day. And where do you get these numbers? You come up to the balanced chemical equation. And the balanced chemical equation shows you for every 1 mole, when there's no number there, you think of the number 1. For every 1 mole of nitrogen, you make 2 moles of ammonia. Again, the coefficients, the number that goes in front is the molar ratios. In this case, 3 moles hydrogen, 1 mole nitrogen makes 2 moles of ammonia. So if we come down here, we know for every 1 mole nitrogen, we make 2 moles of ammonia. These are exact numbers. Therefore, they play no role in the significant figures. Here I'm 3. I should end up with 3. And let's go back to my spreadsheet. Hopefully it's being nicer to me. Let's try once more. Oh, what did I do? Now it works. Don't ask me why. Now this one, I'm going to keep in column A because I'm going to round off at the end. But now I'll round this off at each step. And the answer is 11.1 moles of nitrogen. Am I done? No, I want to get to grams and I'm at moles. So now I have to do step 3. That's moles of B. Sorry, this is getting crowded, to grams of B. And here we have 11.1 moles of nitrogen. What do we want to get to? Grams of nitrogen. Remember, 1 mole of a compound equals its molecular weight. Nitrogen molecular weight 2 times 2 nitrogens, 2 times 14.0 equals 28.0. And we'll need this number. Why? Because it's time to, again, to use your good buddy, your good friend, unit analysis. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. Where do I get that number? Well, first of all, I do this. One mole equals the atomic weight or the molecular weight of nitrogen gas, N2. Notice moles cancel out. I'm left with grams. That's an awful arrow. And now I can go ahead and pick up my calculator. And if I round this off to 3 significant figures, this would be 310. This would be 311. On a test, both answers would be correct because I'm not going to force you to do rounding off the way Dr. White does. So over here, oh, either one would be correct. And that's how you do it. Well, wait, this should be 310. So either 311 or 310, and that's how you do it. Now, one of the questions is, why learn this stuff? Suela, I'm going to have to move on today. Either come to my office hour or also next Monday, I'll be going through the practice problems and we'll do more of these, okay? And thank you for your question. Now, let me, I'm checking the chat and seeing people getting the right answers. Thank you. All right. Now, one of the questions is, why are we doing this stuff? Why are you crinkling your nose? Well, I do that. Why are you doing this stuff? What good is it? How does it affect me? Well, let's go somewhere where most Americans never go to. This is the inside of a chemical plant, or one unit in a chemical plant. This one happens to be in Louisville, Kentucky. Let me just check with I haven't done it all day, but I should now. Thumbs up, people. Can you see the picture? Thank you. And normally you're never allowed to take pictures inside a chemical plant, but this one I did, and I'll explain later in the semester how. But to give you an idea of the scale here, this right here is a forklift truck, and that's the size of a small four-door car. These silver things are called reactors, and reactors are where we run chemical reactions. Just like you have at home a pot where you cook in, we make chemicals in reactors. These two, K and L, different companies name their reactors differently, are huge. They're about 2 stories high, and each one holds the same amount of chemicals when you run a reaction as 4 tank wagons. I think you're all familiar. I showed you the picture of the vehicle that delivers gasoline to gas stations, and also they do milk. That's the same ones, different ones. But those hold 40,000 pounds, 5,000 gallons. So when you do a reaction, one of those reactors I showed you, that's 4 of them. That's 20,000 gallons, or about 160,000 pounds. Now, I happen to be lucky enough that when they built this, I was the chemist who was asked, because of my position in the company, to help commission this. In other words, help start it up, which is a great honor and very rare. I've done it twice in my career. The small part, this plant, when it was built, the small little unit, cost about $100 million. And like I said, this is in Kentucky, and these are huge. And I helped start it up successfully. Let's do one more picture. In case you're wondering, first of all, thumbs up, people. You see me? That's me, Dr. White. And here I am. You notice I'm standing at the bottom of this, I'm 6 foot, or sometimes 5'12", and I'll talk more about it. When I first came here before they started it, by the way, this is one of the cleanest chemical plants I ever worked in, but even then things happen. You can see on this post where a pipe broke or a hose broke, that's chemical on there that hardened. They just wash down the floors with water. That's why it's wet. But over here, let me ask a real question. Can everybody see my pointer moving on the picture? Okay, thank you. When I first got there, a week before they were going to open up, I went down there early to help to learn how certain equipment and controls work. This right here is a way of taking a sample. You know how you take a little rice, is it done? Well, take a sample, a chemical test, is the reaction done? It's not that easy. and they had a different design. I looked at that and said, that's going to give us a tremendous amount of problems. We got to change it. The plant manager and the chief engineer, Dale Robertson, listened to me. They agreed, wow, you're right. That's because at this point I already had about 20 years experience working in chemical plants. And it made our life a lot easier when they redesigned this the way I suggested. How big are these? Let me get another picture open. Here I am walking to the top of that one of those reactors. I'm on, like if you walk from the ground to the first story of a building, one floor up, and I got a second one to go. You're pretty high up, and sometimes you'd have to go up there in a reactor in a chemical plant. These are open grid. You can see all the way to the bottom. You don't like heights, you don't want to be in a chemical plant. But anyways, when you do reactions in a reactor, like I'm showing, you use the exact same calculations to figure out what goes in the reactor. How much of this chemical, how much of that, to make how much of the product. And for this one, you're usually talking about $150,000, $200,000 in chemicals. And trust me, you get fired like that if you mess up once and blow almost $250,000. I never did, because the type of calculations you saw me do, I would do it, and then I'd do it well in advance, because what part of my job was to write what you would call procedure. At certain companies, they call it procedures. At this company, they call it recipes, and to what the workers have to do. And I had to do those calculations, and a week or two before they were going to run something, I'd do it, leave it alone for about 2 days, sit down and do it again fresh, look at my two results. They better be the same. They always were. But when you're dealing with that amount of money and also responsibility, you make sure you do things right. Because if you mess up, you could also kill people. Luckily, that never happened at that plant or anything I was ever involved in. All right, it's time to move on. We did this, we did our, now, calculating the amount of substance taking part in a chemical reaction, we did that. Now, usually one is used up and the other is our excess. Now, this has a special name, and this is called calculating the moles of a product from a limiting reactant. See board, well, you'll see the screen in a second. This is called limiting reactants. Sometimes my Freudian slip, I call them limiting reagents. That's wrong. It's limiting reactants. Here I have a pen, which I don't use my red pen for grading anymore because nothing's getting to me from you on paper. But you notice, let's assume I'm a company and I make these pens. And for simplicity, the whole pen unit that you would buy is made up of a cap and the main unit. And I put the cap on here, and now I can sell it to you. Now, if I had 10 of these and only 5 of those, how many pen units can I sell you? Good question. And the answer is 5, because I only have 5 of these. Even though I have 10 of these, every one of these goes on one of these to make the whole unit I can sell. So this is limiting. Once I run out of these, I can't make any more total units. And that's the concept behind limiting reactants. How something runs out and all of a sudden you can't react it anymore. So let's take a look at how you deal with that. Now let's look at this. How many moles of water are produced if you react 10.0 moles of hydrogen gas with 10.0 moles of oxygen gas? Now it turns out you have to do 2 steps. Now, I used to teach it one way, and a couple of years ago, I had a very smart student, and he came up with a better way of doing it, which works, and I now adopt that way. Now, first of all, as you know, what are we being asked to find? Moles of H2O. What are we given? Moles hydrogen, moles of oxygen. Now, the 2 steps are, each step and I think I spelled calculate wrong, but I was always first. And what you do is calculate the moles of product formed from each reactant. In other words, for hydrogen, all the hydrogen reacted, how many moles of water would you form? If all the oxygen reacted, how many moles of water would you form? And the larger number, 3 dots like this means, and therefore, actually I said it wrong with the, and here, the number, the step of these 2 steps with the smaller number is your answer, because that's the one that runs out first. So let's do our 2 steps. Let's do hydrogen first. And we want to go from moles of hydrogen to moles of water. And it's time again to use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top. If I can write it. Whatever we're trying to get rid of goes here. Where do we get these numbers? From the balanced chemical equation. For every 2 moles, remember the coefficients are molar quantities, for every 2 moles of hydrogen reacting with 1 mole of oxygen, you make 2 moles of water. Therefore, for every 2 moles of water, we need 2 moles of hydrogen. Moles of hydrogen cancel out. Hold on while I get my calculator. That was fast. And you get 10.0. These are exact numbers, 3, 3. This is number 1 step or calculation. Number 2, the other reactant. Again, you want to figure out how many moles of the product. The smaller number was 1 and 2 is your answer. And now, again, we'll use unit analysis. Whatever we're trying to get to goes on top. whatever we're trying to get rid of goes underneath. And now where do we get these numbers? You look up here and notice for every 1 mole, remember when there's no number here, it's the number 1. For every 1 mole of oxygen, you make 2 moles of water. So for every 1 mole of oxygen, you make 2 moles of water. Let me get my calculator out. Hold on. Now, which of these is smaller? This is the smaller one. Therefore, this is your answer. And that's how you do limiting reactants. Now, some teachers give it to you in grams, so you got to convert grams to moles and then moles back to grams. I don't do that. Dr. White likes to be nice. Now, I'm only going to do one of these right now because I want to finish the whole chapter today, because this way we'll end up all the material that will be on test number 2. That's a week from this Thursday. Let me remind you, quick public service announcement from me, Dr. White. Tomorrow, I'll do chapter 6, practice problems. On Wednesday, I'll do chapter 7, balancing chemical equations, practice problems. I'll wait until Monday to do chapter 8, the ones we've just done, because you may need a little more time. And that gives you the weekend to work on that. Don't forget to study the other stuff for the test coming up. And let's move on. Now, there's a very, very, very important concept in chemistry called the percent yield. And percent yield tells you an indication how good did your reaction go. The higher the percent yield, the better it went. In real life, when you mix 2 things together, that was hokey. When you do it in a chemical plant or lab, it doesn't all go 100%. It doesn't. That's life. In fact, organic chemistry, most of the things you try in a lab don't work, like 90%, and you got to be, how should I say, well suited to accept failure and continue to press on, which good organic chemists do. But percent yield tells you how well something happens, how good the reaction is going, how much you've made. When we talk about percent yield, there are a couple of terms, and I won't put this on the test, definitions. Theoretical yield is the amount of product you'd expect if all the reactants were converted to the product, according to mole ratios. In other words, you made everything you expect to. Actual yield is the amount you collected or obtained when you finished in real life. And percent yield is actual yield divided by theoretical yield times 100. Percent yield, actual yield divided by theoretical, this is in weight, grams or pounds or whatever, times 100. The higher this number, the better it is. In industry, oh, one thing, switches off for percent yield. I won't put it on a test, but in industry, when you do a reaction or you want to take a reaction to a chemical plant, you have to have a percent yield 90 or above. Unless you're in pharmaceuticals, then you can get down to 85. But in industry, like what I've worked in, if you're not 90 and above, management will say, we can't make enough money off that. And as for those who saw when I talked about how to reduce test anxiety, I talked about how I brought a reaction that everybody could only get 50% up to 97. Oh, that still makes me feel good. Damn, that was good. Still is. But anyways, 97%, that was pretty good. And when we went to the plant, that got 97%. Let's see. Quick thing. One of the things you don't know, but I've been trained in, part of my training, is called process development. And you saw that big reactor that had 160,000 pounds. We just don't say, oh, I've done it in the lab, let's go there. No, it's called scale up. Now think about if you were in your home and you were making breakfast for yourself or maybe someone else, you'd make a couple of scrambled eggs. Okay, say 2 or 4, whatever. Not that bad. Now say you had 10 or 20 people coming over. Now you've got to do a lot more. You either have to have a couple of frying pans to make your scrambled eggs. You've got to open up a lot more eggs, which takes more time. Now, instead of 10 people, what if you had 10,000 people you have to cook the scrambled eggs? Now you got to do a lot more calculating, and it's a lot longer. Well, in chemistry, it's the same way. If I mix a couple of grams together, it's easy to do. In chemical industry, we have what's known as a pilot plant, where you can scale it up, do it bigger, and then you take it to the plant. And a pilot plant, you work with about 500 pounds, 50 gallons. And then when you take it to the plant, you're doing anywhere from 5,000 to 20,000 gallons. Things take longer, and you have to take that into account, which when you saw me at that chemical plant, when I write a procedure, when you say put in 5 milliliters something, instantaneous. When you have to transfer 10,000 gallons, that takes about an hour depending on the pumps you have. And you have to figure that all in. And that's called process development, which I'm well trained in. And I just thought I'd give you that little insight. And with that, I have finished everything I want to talk about for test number 2. Tomorrow I'll go through the problem set from chapter 6. Wednesday we'll do balanced chemical equations. Ooh, quick public service announcement. Don't forget today, the lab for balancing equations I went through last Thursday is due today. I'll put out an announcement since on Thursday I'll be going through, well, I won't go through those answers, maybe I will. I'd like everybody to should get it in today, but by Thursday morning before I start lecture, have that lab into Blackboard. If you haven't noticed, I've caught up with labs. And if I look at the clock, wow, time flies when you're having fun with chemistry, which is a good thing. With that, I'll say, gehen gesund, be healthy. Goodbye.